A non-integer representation uses non-integer numbers as the radix, or basis, of a positional numbering system. For a non-integer radix I²1, the value of is. The numbers d are non-negative integers less than I². This is also known as AI² expansion, a notion introduced by Ra. Copyright me and first studied in detail by Parry. Every real number has at least one I² expansion. There are applications of I² expansions in coding theory and models of quasicrystals. Construction: I² expansions are a generalization of decimal expansions. While infinite decimal expansions are not unique, all finite decimal expansions are unique. However, even finite I² expansions are not necessarily unique. For example, I+1 equals I2 for I² equals I, the golden ratio. A canonical choice for the I² expansion of a given real number can be determined by the following greedy algorithm, essentially due to Ra. Copyright me and formulated as given here by Frufni. Let I²1 be the base and x a non-negative real number. Denote by our is Hakshaw the floor function of x, that is, the greatest integer less than or equal to x, and let x equals x a our is Hakshaw be the fractional part of x. There exists an integer k such that I² k a per mil currency x, I² k plus 1. Set. And. For k a1 a per million j, a, put. In other words, the canonical I² expansion of x is defined by choosing the largest dk such that I² k dk a per mil currency x, then choosing the largest dk a1 such that I² k dk plus I² k1 dk a1 a per mil currency x, etc. Thus it chooses the lexicographically largest string representing x. With an integer base, this defines the usual radix expansion for the number x. This construction extends the usual algorithm to possibly non-integer values of I². Examples: base IC golden ratio base 11i equals 100i. Base e, with base e the natural logarithm behaves like the common logarithm as ln, 1e, equals 0, ln, 10e, equals 1, ln, 100e, equals 2 and ln, 1000e, equals 3. The base e is the most economical choice of radix I²1, where the radix economy is measured as the product of the radix and the length of the string of symbols needed to express a given range of values. Base I euro can be used to more easily show the relationship between the diameter of a circle to its circumference. Since circumference equals diameter I euro, a circle with a diameter 1 I euro will have a circumference of 10 I euro. A circle with a diameter 10 I euro will have a circumference of 100 I euro, etc. Furthermore, since the area equals I euro a, radius 2, a circle with a radius of 1 I euro will have an area of 10 I euro, a circle with a radius of 10 I euro will have an area of 1000 I euro and a circle with a radius of 100 I euro will have an area of 100,000 I euro. Base IH2 behaves in a very similar way to base 2 as all one has to do to convert a number from binary into base IH2 is put a 0 digit in between every binary digit. For example, 191,110 equals 111,011,101,112 becomes 101,010,010,010,010,010,010,010 IH2 and 511,810 equals 10,11,111,111,102 becomes 100,000,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010,010, without the need of a decimal point. The base can also be used to show the relationship between the side of a square to its diagonal, as a square with a side length of 1/2 will have a diagonal of 10/2 and a square with a side length of 10/2 will have a diagonal of 100/2. Another use of the base is to show the silver ratio, as its representation in base/2 is simply 11/2. Properties: in no positional number system can every number be expressed uniquely. For example, in base 10, the number 1 has two representations, 1.000 and 0.999. The set of numbers with two different representations is dense in the reals. but the question of classifying real numbers with unique I-squared expansions is considerably more subtle than that of integer bases. Another problem is to classify the real numbers whose I-squared expansions are periodic. Let I-squared 1, and q, I-squared be the smallest field extension of the rationals containing I-squared. Then any real number in 0, 1, having a periodic I-squared expansion must lie in q, I-squared. On the other hand, the converse need not be true. The converse does hold if I-squared is a Pisot number, although necessary and sufficient conditions are not known. See also, beta encoder, non-standard positional numeral systems, decimal expansion, power series, Ostrowski numeration, references, Bigiad, Jan, Distribution modulo 1 and Diophantine approximation, Cambridge Tracts in Mathematics 193, Cambridge, Cambridge University Press, ISBN A978-0-521-11169-0, ZBLA Prio 6066616, Burdick, or. Frufny, C.H. Gazzo, J.P. Krijar, R., Beta Integers as Natural Counting Systems for Quasicrystals, Journal of Physics. A Mathematical and General 31, 6449 Euro 6472, doi, 10.1088311011, ISNA 0305-4470, MRA 1644115A. Frufny, Christiane, How to Write Integers in Non-Integer Base, Latin 92, Lecture Notes in Computer Science, 583/1992, Springer Berlin/Heidelberg, PPA 154 Euro 164, doi, 10.1007/BFB00238826, ISBN A978-3-540-55284-0, ISNA 0302-9743A. Glendinning, Paul. Sidorov, Nikita, Unique Representations of Real Numbers in Non-Integer Bases, Mathematical Research Letters 8, 535 Euro 543, doi, 10.4310/MRL 2001 V8N4A12, ISNA 1073-2780, MRL 1851269A. Hayes, Brian, Third Base, American Scientist 89, 490 Euro 494, doi, 10.1511/2001.40.3268A. Katz, William H., Fibonacci Codes for Synchronization Control, Institute of Electrical and Electronics Engineers. Transactions on Information Theory, IT 11, 284 Euro 292, ISNA 0018-9448, MRO 191744A. Parry, W., On the I-squared Expansions of Real Numbers, Acta Mathematica Academiae Scientiarum Hungaricae 11, 401 Euro 416, doi, 10.1007/BF020200954, ISNA 0001-5954, MRO 142719A. Petkovanec, Marco, Ambiguous Numbers are Dense, The American Mathematical Monthly 97, 408 Euro 411, doi, 10.2307/2324393, ISNA 0002-9890, MRA 1048915A. Ra Copyright NE, Alpha Copyright D, Representations for Real Numbers and Their Ergodic Properties, Acta Mathematica Academiae Scientiarum Hungaricae 8, 477 Euro 493, doi, 10.1007/BF020203331, ISNA 0001-5954, MRA 00973774A. Schmidt, Klaus, On Periodic Expansions of Pisot Numbers and Salem Numbers, The Bulletin of the London Mathematical Society 12, 269 Euro 278, doi, 10.111212.4.269, ISNA 0024-6093, MRA 576976A. Further reading, Sidorov, Nikita, Arithmetic Dynamics, Inbizugel, Sergey. Kolyada, Sergey, Topics in Dynamics and Ergodic Theory. Survey papers and mini-courses presented at the International Conference and US-Ukrainian Workshop on Dynamical Systems and Ergodic Theory, Katsavli, Ukraine, August 21 to 30, 2000, Lond. Math. Soc. Lect. Notes 310, Cambridge, Cambridge University Press, PPA 145/189, ISBN A0-521-53365-1, ZBLA 1051.37007 External links, Wellstein, Eric W., Base, MathWorld.